Section 12.4, the cross product. Recall that we defined what it means to take a scalar and multiply a vector. For example, scalar c times a vector v just moves the, well, it doesn't really move the vector so much. It makes it bigger, smaller, or changes the direction backwards. Then we said that we could take two vectors, let's say v and w, and dot them together, and we would end up with some scalar in the end. But what if we wanted to take two vectors v and w and we wanted to make a product out of them that results in another vector, say u? Well, then we wouldn't use a dot because we already used the dot. Instead, how about we use a cross, and we can call that cross product this thing. So you might be saying, okay, well, why would you define it in such a weird way? You have to take these specific components of the vectors, multiply them, and then subtract them, and it's this whole mess. Well, I think it'll become a little bit more clear later on the advantages of this particular cross product. It actually works out in such a way that it has a few cool geometric properties. But for now, let's just play around with actually trying to figure out some way to compute this and actually remember this thing, because using the definition, I don't even want to read it to you, it's so long. So first, let's define what it means to have a determinant of order 2. So we represent the determinant using this matrix, and then we use these straight vertical bars on the side of the matrix to say we're taking the determinant. If we were to just write a matrix using parentheses or using brackets, then that would just be a matrix without taking the determinant. But when we put the vertical bars, we're saying do a times d minus b times c. So just multiply the diagonals and subtract. Then we can define a determinant of order 3 by taking many determinants of order 2. So what we do is we take a1 and we multiply it by the determinant of the components that are not next to a1 vertically or horizontally. So that means all of these guys become the determinant, or become the matrix that forms what we want to take the determinant of, multiplying by a1. So that becomes our first term in our determinant of order 3. What we do is we take a1, we multiply it by b2 times c3 minus b3 times c2. And then we take a2 and multiply it by a determinant of a matrix formed by components that are not right next to a2, vertically or horizontally. So that would be, maybe I'll make it square, b1 c1, b3 c3. So that becomes this matrix over here. We take the determinant, so that's b1 times c3, b3 times c1. Notice you have to be a little bit careful. Over here we left a1 positive. In our last term we're going to leave a3 positive. But a2 we make negative. We always make the middle term of our determinant of order 3 negative. Lastly, we have a3, so that multiplies by the determinant of this matrix, which is this. And then the cool thing about knowing what a determinant of order 3 is it turns out that that's what the cross product is. You just make your top row ijk instead of a1, a2, a3. And then the other two vector components form rows 2 and 3. And then you apply the definition of the determinant of order 3. So I gets multiplied by this matrix. Then you take minus j, circle it, times this matrix. That's this guy. And then you take k times the last one. And by matrix I mean determinant of the matrix. So let's do an example real quick of computing a cross product. How about we have these two vectors, 1, 3, 4, and 2, 7, minus 5. So I can say that A cross B is going to be I, J, K in our first row, and then 1, 3, 4, because that's A in our second row, and then 2, 7, minus 5 from B in our third row. So then this just equals, let's see, we have I times this matrix, the determinant of that matrix. So that's going to be 3, 4, 7, minus 5 times I, and then we'll have a minus sign for our middle one. We always have minus for that. So then j will be times this matrix, so that's 1, 4, 2, minus 5. So 1, 4, 2, minus 5 times j. And then last but not least, we'll do k, so that's this guy. So 1, 3, 2, 7. And times k. Alrighty, so when we multiply our diagonals and subtract, we get 3 times negative 5, which is negative 15. Then minus 4 times 7, which is 28. So that's what our I coefficient is. Then we subtract 1 times minus 5 minus 2 times 4. So that's minus 5 minus 8. And then for k, 1 times 7 minus 3 times 2. So that's 7 minus 6. So that means that our cross product becomes negative 43i plus 13j plus k. So you could write that without ijk notation as negative 43, 13, 1. One of the first cool things about cross products we'll do is that the cross product of any vector with itself is 0. So let's look at an arbitrary vector A. Let's say that that's A1, A2, A3. Then the cross product A times, or A cross A, will be equal to I, J, K crossed with A1, A2, A3. And then the second row is the same because I'm doing the same vector twice. So A1, A2, A3 again. Okay, so let's multiply this out. We get that this is equal to I times this guy, so that's A2, A3 minus A3, A2. So you can already see what's going to happen. And then the second one is the j, guys. So that's this one. So A1, A3 minus A1, A3, or A3, A1. Do you want to preserve the order? But notice the order is not going to matter because all of these little a's are not vectors. They're components of vectors, so they're just components of vector or scalars. So commutativity is no problem. We'll just switch the order. So then for k, we've got A1, A2 minus A2, A1. And that just becomes 0 for this one because just switch the order for A3 and A2. And you've got A2, A3 minus A2, A3. So we have 0i. And then for j, same thing, it's 0. And then for k, it's also 0. So that's just the 0 vector. So notice that whenever you want to prove one of these properties, if you can't think of a trick, it's usually good to write an arbitrary vector in terms of arbitrary components, and then just multiply things through if you need to multiply or whatever you need to do, and then see what you get in the end and hope it's what you wanted to prove. Okay, how about the vector A cross B and its relationship to A and B? Turns out it's orthogonal or perpendicular. So that means that if we look at vector A and we look at vector B, then the angle between A and A cross B is 90 degrees, and the angle between B and A cross B is also 90 degrees. So that's kind of cool. The way that we can prove that is using what we call a scalar or triple product. So what we do is we take A cross B and we dot it with A. So what that does is it takes A and it puts that in the first row. And then the second row is our vector A, because it's part of our cross product. And our third row is B. So then notice you get A1 times this thing. You get A2 times this thing with a minus sign, etc. Notice this is the same thing as putting ijk in the top row and then dotting the vector later with A. It results in the exact same thing. It doesn't make a difference. So we end up with each of these guys. Each of these determinants can be multiplied out. You multiply and subtract and we get these guys. And then we distribute inside each one. And then notice what happens if each of these is the same. Oh no, those weren't. Sorry. Here's B3. So I need to look at the matching B3 one. So this one is the same as this one. So they don't directly cancel, but they do cancel. Alright, so A1, B2 was a little bit too optimistic. But we just have to look a little bit carefully, and then we can see they do cancel. And we end up with 0, in this case the 0 scalar. Remember that when your dot product is 0, you're perpendicular. So, kind of cool. Any cross product will be perpendicular to its two, I guess, factors, if you want to think of it that way. By the way, remember that even though the cross product of any vector with itself is 0, the dot product wasn't. The dot product of any vector self was the length squared, the magnitude squared. So the properties of the cross product are going to be a lot different than the properties of the dot product, which makes sense because the cross product is a vector and the dot product was a scalar. Also, we define them totally differently. So if theta is the angle between A and B, it turns out that we do have an identity similar to the dot product one. However, even though it uses an angle, it uses sine instead of cosine, but also it doesn't actually use the cross product itself, it uses the magnitude of the cross product. Remember, we're looking at the sine of an angle, and we're looking at lengths, so we're looking at scalars. So we wouldn't just be able to throw the cross product on the left side because we can't have a cross product equal scalars, it has to equal vectors. But we can take the length of a vector, and that's a scalar, so we put these lengths in. Proving this is not too bad. You just go straight through and, chug away at, or chip away at just evaluating this thing for an arbitrary vector. So A cross B squared, the length of A cross B squared, you can work out is literally just this mess. Because remember that this is basically what A cross B is. Instead of A1, A2, and A3, you just put an ijk. So that means that these are each of the components. So just square those, and that gives you the magnitude squared. The square root will cancel because of this square. Okay, so then you have to FOIL each of them out, and it's a mess. It's horrible, it's unholy. So you FOIL each of those out, and then it turns out that you can factor the two sides. So you factor this over here, and this over here. It's not very pleasant, but you can do it. And then you end up with this is literally just the length of A squared. This is literally just the length of B squared. And this is just the dot product of A and B. So you look, A, B, yeah, dot product. So the dot product squared, well, the dot product is just length of A, length of B, cosine theta by our previous formula. So dot product squared is just each of those things squared. So what we can do is we can take cosine squared and write it as, well, before we even do that, we've got an A squared, B squared in both these terms. We can factor that out. And then we've got 1 minus cosine squared, which we'll write as sine squared. then notice we have a square on the left, we have a square on the right. Just take the square root of both sides and you end up with what we wanted to prove. Oh, just a quick housekeeping. Remember that the square root of sine squared will be sine theta only in this case. Otherwise, it'd be plus or minus, because in this case we have theta between 0 and pi, because that's what we stated as one of our hypotheses for our theorem. So that's what forces everything to work out nice and be positive. Okay, our next corollary for this is that the cross product of any two vectors will be 0 if those vectors are parallel, and vice versa. So they're parallel if and only if the angle between them is either 0, so they're both lined up, or it's pi, so then we've got vectors like that. Either way, they're parallel in those two cases, and we have sine of 0 or pi is 0, so that forces the cross product to be 0. That argument works both ways, so you get the if and only if all at once. The length of the cross product is then equal to the area of the parallelogram determined by A and B. So this is kind of cool. If you take a vector A and you take a vector B and you draw them so that both of their tails are together, then what you can do is draw a parallelogram, as we've seen. So then the height of the parallelogram would be the magnitude of B times sine of theta, because remember, sine is opposite over hypotenuse. So if this is, let's say, x, and I wanted to solve for x, then x, then sine of theta would be x over b. So then multiply with the length of b. So then multiply that by sine theta, and you'd solve for x. So that's what this height is. Okay, cool. So that means the area of the parallelogram is this length times this height. So that's length of A times length of B times sine theta, which is literally just the cross product, as we've proved. Okay, how about we find a vector perpendicular to the plane that passes through 3 points? So we have points, we need vectors if we want to do cross product, because remember, the cross product is perpendicular to both of the vectors you put in. So it'd be nice to have some vectors to put in. So how about we figure out what vector PQ is through the points PQ? Remember, we can build vectors through points by subtracting. So we take all of the points for Q, and then we subtract the corresponding components for P. So we did -2, -1. And then we'll have, that's I. Then we'll have 5 minus 4 for J. And then we'll have -1 minus 6 for K. So that's -3I plus J minus 7K. So how about PR? We'll do the exact same thing. We subtract, we get 1 minus 1I plus -1 minus 4J plus 1 minus 6K. So that's minus 5J minus 5K. Okay, now we can take the cross product, and that'll be perpendicular. So let's do PQ cross PR now that we have vectors. Stick in. So we get IJK in the top row. And then we've got our first vector, -3, 1, -7, and then 0, -5, -5. So that just becomes I times this minus this. So that's -5 minus 35 times I. And then minus for J, that'll be these guys. So that's -15 minus 0. We multiply and subtract. And then we've got K, which is +15 minus 0. So that just works out to be -40I minus 15J plus 15K. So that's a vector perpendicular to the plane that passes through those points. So what you can do is you can go back to this picture, think about these two vectors over here, and think of them lying in this flat little screen, and then the vector that is the cross product is kind of popping out of the screen towards you. So I can't really draw that. You kind of have to imagine that. And I could no, I can't draw it. You got to imagine this popping out, hitting you right in the eye. And it's perpendicular to the plane. And that's the cross product. Okay, so this is kind of cool. We can actually find the area of a triangle, that means, because we can take the cross product we just computed, PQ cross PR. We said that that was minus 40, minus 15, 15. And by the way, any scaled version of this cross product would have been perpendicular to the plane. We could have multiplied it by 2, divided by whatever, it doesn't matter, it would have still been perpendicular. But we want this one right now because the magnitude of this, remember, is the area of the parallelogram that's spanned by these vectors. So the magnitude of this is minus 40 squared plus minus 15 squared plus 15 squared. So that's just 5 times the square root of 82, 5 radical 82. So the area of the parallelogram is 5 rad 82, so the area of the triangle is half of that. Just cut the parallelogram in half. So that's 5 over 2, square root of 82. Okay, it turns out there's a bunch of properties of the cross product similar to properties of the dot product, but not the same. Notice that if I take I and I cross it with J, then that's equal to the length of I cross J would have to be the length of I times the length of J times the sine of the angle between them. So the sine of the angle between I and J is 90. So that's just 1. So I cross J has to be equal to the length of I times the length of J, which is 1 times 1. So it's got to be a vector that's perpendicular to both I and J with length 1, so that's K. Notice that similarly J cross K would have to be I, and K cross I has to be J. However, if I want to do J cross I, then I'm looking at, well, here's I, right? That's on the x-axis. Here's J on the y-axis. The angle is this way between J and I. So it's not 90 like this one was. It's 270. So the sine of 270 is minus 1. So that means that J cross I will be minus K. Similarly, K cross J will be minus I, and I cross K will be minus J. So the cross product is not commutative. So it's not like the dot product. Dot product was commutative. We could switch the order. We can't switch the order of the cross product. We can sort of, though, because it's anti-commutative, notice. Instead of plus, we just put a minus, and then we can switch the order. So A cross B is minus B cross A. Also notice that if you were to take I and cross it with I cross J, then, well, we just said I cross J was K, so that's I cross K. And we said I cross K was minus J. But if you were to switch the parentheses and put them around the I cross I, and then cross it with J, then I cross I, well, the dot product of any, the cross product of any vector with itself is 0. So that's 0 cross J, which is the 0 vector. So it's totally different. So the cross product is not associative. Very nasty. But there are a couple things. It turns out that we can take scalars and we can factor those out, which is nice. And we can put the scalar in the other, multiply it by any of the other vectors, or just the other vector is only one. We can also distribute the crossover addition. We can also distribute addition over the cross product, so A cross C and then B cross C. We can also say that the scalar triple product, A dot B cross C, can be moved. So if you have A dot B cross C, you can interchange the dot and the cross, which is kind of cool. So that might be worth proving, but you can just prove all of these pretty easily by writing out each of the vectors in terms of arbitrary components and then just doing whatever operation you have to do and hoping it works out, which it will. Just a little messy. Lastly, the kind of cool thing is that if you take A cross B cross C, which is basically this guy over here, so you do the cross product twice, you can actually switch it into something involving the dot product. So A cross B cross C is A dot C multiplied with B, because A dot C, remember, is a scalar, so it's a scalar times B and a scalar times C. Pretty cool. The volume of the parallel pipette determined by the vectors A, B, and C is the magnitude of their scalar triple product. So that means that what we're doing is we are taking the determinant, that's these smaller two bars, and then after we take the determinant, we're taking the length. Because after taking the determinant, we're going to get a vector, and we want a scalar. So this is just like how we did the length of the cross product to get the area of a parallelogram in 2 dimensions. Turns out if you want the area of a parallelepiped, a 3-dimensional parallelogram, then you just do the length of the scalar triple product. So you just have to throw in a dot. And if the volume of this thing is 0, then that means that this vector that's not, well, any of the 2 vectors, any of the 3 vectors are not pointing out in another direction of another plane. Instead, they're all together in the same plane. So it's actually kind of hard to draw, but it means that if the volume of the parallelepiped spanned by any 3 vectors is 0, that means I can draw all of those vectors together. So let's prove this real quick. We have the geometric interpretation of the scalar triple product in our figure. The area of the base parallelogram is just the length of the cross product, as we said, B cross C. So then we want to try to figure out what the volume of this thing would be. So let theta be the angle between A and the cross product B cross C. Remember, the cross product is perpendicular to the other 2 vectors, so it stands up straight out of that plane on the bottom. If the plane is the floor, then the cross product goes straight out from the floor. Okay, so let theta be that angle, and then the height of the parallelepiped, h, would be the length of A times the cosine of theta. Because if theta is this little angle over here, then the length of A is the hypotenuse, so that means that this is the adjacent side. So that means the cosine of theta is h over A, length of A, and then you can just multiply to get that h is equal to the length of A times the magnitude of, or the absolute value of the cosine theta. Okay, so then you just take that height and multiply it by the area of the base, and that gives you the volume of your parallelepiped. B cross C times the length of A times cosine theta is just what the scalar triple product is. Notice all we're saying is we're taking this B cross C cosine A, that's the cross product, and then we're basically dotting it with this A over here. Okay, let's do an example. How about we take the scalar triple product and show that the vectors A, B, and C are coplanar. So we'll take A dot B cross C. That dot's kind of hard to see. And that's just going to be the cross product where A is on the top row instead of ijk. So 1, 4, minus 7 goes on top, 2, minus 1, 4 goes in the middle, and 0, minus 9, 18 goes in the last row. So this just equals 1 times the determinant of minus 1, 4 minus 9, 18, minus, because we still have a minus in the middle, so minus 4 times the determinant of 2, 4, 0, 18, and then minus 7 times the determinant of 2, minus 1, 0, minus 9. So that just equals 1 times 18 minus 4 times 36 minus 7 times minus 18, which is 0. So because our scalar algebra product is 0, the volume of the parallelepiped spanned by these vectors is 0. And if the volume of the parallelepiped is 0, then that means that the vectors must be coplanar. If we have a vector F, and it's the force acting on a rigid body at a point given by a position vector r, then the torque vector tau, relative to the origin, is defined to be the cross product of the position and force vectors. It measures the tendency of the body to rotate about the origin. So then there's a theorem we have that the magnitude of the torque is equal to the magnitude of r times the magnitude of F times the sine of theta. But that's pretty easy to prove because the magnitude of the cross product is just equal to that, as we've seen. As an example, let's say we have a bolt. It's tightened by applying 40 Newton force to a 0.25 meter wrench as shown in our figure. Let's find the magnitude of the torque about the center of the bolt. So the magnitude of tau is equal to the magnitude of r cross F. So that's just the magnitude of r times the magnitude of F times the sine of the angle between them, which it says is 75 degrees, so we'll take the sine of 75 degrees. And that equals 0.25 times 40 times the sine of 75 degrees. So that equals 10 times the sine of 75 degrees, which is approximately 9.66 Newton meters. They didn't ask us, but if our bolt is right threaded, then we could write the actual form of tau, not just the magnitude. We could take the magnitude of tau, and we could use that to scale the unit vector n, and we could say that that's about 9.66 times n, where n is just the unit vector that is directed down into the page. So instead of popping out at you, it's going away from you into the page. And scaling that scale is exactly what your torque is. It's a vector pointing down into it.